domain protein is leafy.
So I'm not going to talk about leafy. Actually, it's a lot less was for Chinese. We have to. Oh, sorry. This one. Yes. So, so my talk. Very sorry. So my talk. We have to work mainly in crops. So everyone knows nitrogen is one very essential nutrient for plant growth and development. So here's a picture you can see. So even in a low nitrogen condition, plants grow almost yellow, and where you apply high amount of nitrogen fertilizer, all the plants growing green, and you have got a high yield and a high quantity. So, but in China now, most people are working on plant shoot, so the tillering and also the yield. But now we are focusing on the root. But this nitrogen, if regulation of nitrogen on root development actually depends on its concentration and form. So like under nitrogen deficient condition, so the plant normally activate root-free gene responses, which the plant get longer primary root and also more lateral root. And well, when you give more to excessive nitrogen, so it will dampen the plant growth. So especially for the ammonium, so which we call ammonium toxicity. So here you can see compared to nitrate, ammonium can actually reduce the plant's growth and also both on shoot and the root. So and the mechanism has been previously associated with like plant metabolism and hormone signaling, and also like reservoir acidification. Because this is because normally when the cells uptake ammonium, they will also pumping out a photon. The proton will cause the medium acidification. And also recent study also showing that even during the glutamine synthesis, it also produces one proton, which causes the cellular acidification. And also there are works showing that the upper plast acidification would actually increase oxygen imports to the plant. And but rice is very special because it's grow in a paddy field, so it means it prefers ammonium as its major in organic nitrogen sources. And also in this ammonium treatment, we don't see bad growth. So actually, plant grows very happy, even better than the nitrogen treatment. So that means the ammonium. So rice has its specific role to adapt its growth to ammonium. So our question is, how does the root respond to nitrogen, and what's the mechanism? So first we start with the treatment with different ammonium donors. Then we found that this treatment not only inhibit the similar root elongation, but it also induce this helical root response. And so we take a movie to show. So in a nitrogen deficient condition, the plant go down, and but where ammonium stopped and start to cool. To get why they found have this response, we first check so if it's really the root uptake ammonium, and how about the fruiton. So we use this NMT technique, which we show that so the root, when you apply very high concentration of ammonium, so the root get a large amount of ammonium get into the root, and meanwhile it's also pumping out a lot of fructose. And this was confirmed by using the pH indicator BCP, and also we continue to measure the medium pH when we saw when we added this ammonium donors to the medium, the medium is acidic. And when we generate this mutant, which is a callable CRISPR mutant for AMT4 members, and now we found that in this mutant, the ammonium inhibition of root growth and also the induced chemical root response was completely recovered. And so this means this function, so this response actually is associated with ammonium take. And meanwhile, we found that when we add meds, so the pH buffer into the medium, it can also restore the primary root elongation. Meanwhile, it also rescue the root. So you don't see this chemical root response anymore. So it means probably because of the medium pH changes. Meanwhile, we use this BCP staining again, and we saw when you don't add mass, the medium become yellow, means it's very acidic. Well, when you add mass to buffer the pH, then you saw it gets stable, and you don't see this chemical root response. So to mimic this, we also like to adjust the medium pH to low pH. Now we found in the pH 4 condition, we also see this chemical root response. So this all means this actually is the chemical root response is caused to the medium acidification, which is a result of the ammonium uptake. Because oxygen is so important in regulating this root growth tropism, so we also check the DR5 expression in the rice root. And we found that when in the pH, so ammonium treatment, we have it asymmetric distribution of oxygen response in the root tip. Well, when we add mass, we don't see this asymmetric DR5 expression. Well, when we treat the root with low pH, we see it again even stronger. So you can see very strong DR5 signals in the epidermis. So to get a shorter conclusion here, so we found that actually the root acidification is the primary cause of the ammonium-induced chemical root response. This is because when the plant root uptake ammonium, it's pumping out the protons, and this makes the medium acidic, and which then changes the oxygen distribution, which causes this chemical root response. Still, when we check the primary root, even in the mass, when the bust medium buffer condition, we can still see the inhibition of the primary root. So it means the ammonium inhibition on the root elongation only involves some other mechanisms and regulators. To address it, we did a EMS mutant screening for the mutants with a lot altered sensitivity to ammonium. Then we found first we found one mutant which is I23. So it has a missense mutation in D2 domain. So in this mutant, the root is like normally don't respond to ammonium at all. And but interesting, so when we cross DR5 winners to this mutant, and then we saw the DR5 singles completely disappeared from the epidermis. So we don't see the DR5 single anymore, and for which reason we don't know yet. And meanwhile, we also identified another mutant, which is root hypersensitive to ammonium agent, which means in the nitrogen deficiency condition, it is still have seminal root growth, but in a high ammonium condition, the root almost stopped. So it shows hypersensitive to ammonium treatment. And we also actually get a root from the field. So now we check, so in the field, we can consistently see this root phenotype even in the soil condition. And then we check if this root, so the root arrest phenotype is caused to the meristem activity. So we did this MSPI staining, and we found indeed in this mutant, the root meristems become very smaller, and we have less meristem cells compared to wild type on a high ammonium condition. While the root in the root elongation zone, the cell length was not changed. Meanwhile, we use the EDU to detect the cell division activity. We also found it on a high ammonium condition. In this mutant has a very low cell division activity. So this confirms this actually the low mutant meristem is very sensitive to external ammonium. But we found this actually the low sensitivity to ammonium is a lot attributed to ammonium uptake and acidic stress. Well, first we did so with NMT and also nitrate ammonium uptake assay, we found that actually this mutant not really affect the ammonium uptake. Well, we also see is actually in this mutant, the photo release is even less than wild type. This was also confirmed with BCP staining. So in this mutant, we didn't see the changes of the root pH. And then we check the phenotype. So actually, this mutant, the root elongation in this mutant also not really sensitive to pH. Then we start to identify the cause gene of this mutant. And then we by using a mu map, across and a mu map, we found that actually it includes argininosaccharide laces. There's a point mutation in this mutant which causes the loss function of this gene. And now we did a genetic complementary and also make a CRISPR mutant to confirm that this gene actually is the causal gene of the mutant. Then we check the protein localization and also gene expression of the gene, and we found that actually ASL is expressed in all the root tissues, and then it's specific localized to the prostate, and also it's induced. This gene expression is induced by nitrogens and also the promoter gas. We can confirm with the promoter gas staining. Yeah. Now, this gene actually the function is responsible for arginine synthesis. It acts on the urea cycle, so it's convert the glutamine to arginine. So now we check all these metabolites in this cycles. Now we found actually all the precursors of arginine was also accumulated in this mutant. Well, in the products like arginine is reduced in this mutant. So it's confirmed this SLs acts on the biosynthesis of arginine. We also check all amino acids. Now we found in this mutant actually the glutamine accumulate. It's highly accumulated in the root cells, where arginine is a bit reduced. Sorry, Then we did a complementary experiment with all these glutamine and the arginine compounds. Then we found this mutant is still become also sensitive to glutamine treatment. And well, this root elongation can be rescued when you apply this MSO, the inhibitor of GS1.1. And meanwhile, when we add this arginine, then it can also partially regulate the root elongation in the mutant. So this confirms this the SL actually is regulated the glutamine and arginine synthesis to regulate the root response to ammonium. Now, by translational analysis, we found actually this gene suppress oxygen signaling in the mutant. So like oxygen signaling and oxygen transport and oxygen small oxygen RA genes are all reduced in the mutant. And we check the oxygen level is also reduced in the mutant and rescued in the complementary lines. And now the DR5 expression was also reduced in the root meristem in this mutant, and it can be rescued by when you add the arginine. And then later on we pick up one gene pin 1A and it's homolog pin 1B, and make a double mutant. And then we found in the high ammonium treatment they have give this small root which is similar to a low-high mutant. So we think only SL is their role in maintaining expression of pins in the root meristem to regulate root elongation. So just to make a conclusion, so instead, in addition to the technical root response, we also found only a primary result for this root elongation inhibited by ammonium. It's so we found this actually this nitrogen assimilation also become very important to regulate the root response to ammonium. And but how this what the components linking nitrogen metabolism to oxygen homostasis or signaling remains unclear. So now we are working on this project. So for all this work, I have to thank to Dr. Xuan and also a PhD student Jialun Tian who did the most experiment. And I also want to thank Tom for some great support. Thank you.
Thank you, Ray. Any questions or comments?